Usually when we talk about building a modern web application, there's this legacy expectation of manual labor.
Oh, absolutely.
It's like bricklaying, you know? You want a piece of text to show up on the screen, you hand code the HTML for that text.
Right, one brick at a time.
And if you want a high-resolution image to look good on a smartphone, you have to open Photoshop, crop it, compress it.
Upload it to a very specific static directory on a server.
Yeah, and then hard code the file path. It's just so tedious.
But historically, we really relied on that tangible one-to-one relationship, right?
Right.
Seeing the exact file you just uploaded sitting in a visible folder, it felt safe.
Because you could literally point to it.
Exactly. The architecture was rigid, but, I mean, it was predictable.
It is predictable, but it's also incredibly tedious when you actually need to scale a project.
Boy, for sure.
But then you step into the world of modern web architecture, specifically headless CMS platforms paired with modern front-end frameworks, and suddenly that trowel and mortar are completely gone.
Yeah, it's a completely different landscape now.
We're looking at a development environment that feels radically different.
We've basically moved from manually stacking those bricks to, well, essentially writing the blueprints and letting the factory assemble the house for us.
In real time, right.
The infrastructure handles all the heavy lifting now, which allows the engineering team to focus entirely on the application's logic and the user's experience.
So today, we are going to reverse engineer that factory.
Let's do it.
We've got this massive stack of technical documentation and curriculum notes specifically detailing how to leverage Contentstack.
Which is a major player in the headless content management system space.
Exactly. And our mission for this deep dive is to trace the complete life cycle of modern data delivery.
From start to finish.
Right. We want to look at exactly how a headless architecture connects the backend repository to a lightning-fast front-end application.
Like a Next.js app, for example.
Yeah, moving from basic data fetching all the way through global edge networks and automated deployment.
The material here really provides a masterclass in decoupling.
It does.
We're going to explore the precise mechanisms that make this possible. I mean, we aren't just looking at the features here.
No, we're breaking down the actual architectural decisions.
Right, the decisions that enable an omni-channel application to pull dynamic data instantly without overwhelming the client device or the origin server.
So for you listening, whether you are prepping to build a Next.js app, or you're trying to understand modern headless architecture, or you just want to know how the internet delivers data to your phone so insanely fast, this deep dive is going to give you a crystal clear roadmap.
It really demystifies the whole process.
Because we're talking about stripping away the manual generation of HTTP headers, the tedious hand cropping of media assets.
And those brittle deployment scripts that keep everyone up at night.
Exactly. There are highly sophisticated, automated abstractions that handle all of this for you now.
But to understand how those abstractions work, you really have to start at the foundational layer of data retrieval.
The starting line.
Right, which is the SDK.
The software development kit. And in the context of a JavaScript-heavy ecosystem, that means we are looking at the JavaScript Content Delivery SDK.
Yeah, if you are building a modern web app, whether that's React, Vue, Next.js, this SDK is your primary interface with the Contentstack repository.
It abstracts away the raw networking layer entirely.
Completely.
The documentation points out that pulling this into your project is as simple as running a quick npm install Contentstack command in your terminal.
Which is standard for most developers.
Right. But obviously, having the library sitting in your node modules folder doesn't magically get you the data.
No, you have to authenticate first.
You have to establish a secure, context-aware connection to the backend. And this is where we see a very specific authentication triad.
The 3 keys.
Yeah. You initialize the stack using an API key, a delivery token, and an environment name.
And understanding the separation of those 3 keys is absolutely fundamental to grasping secure headless architecture.
Okay, let's break that down.
So your API key is basically the master identifier for the overarching container.
What Contentstack literally calls the stack.
Right. It tells the system, hey, I am trying to talk to this specific corporate account and this specific project.
But the API key alone shouldn't grant you access to read the data.
Exactly, because it lacks context.
Let's drill into that context for a second, because usually developers are used to just passing a single bearer token in an authorization header and calling it a day.
Yeah, the old way.
So why the hard separation here between the API key and the delivery token?
Well, it comes down to isolating the blast radius and strictly enforcing architectural boundaries.
Blast radius is a great way to put it.
Because a single project doesn't exist in a vacuum, right?
Yeah.
You have your live production website, sure, but you also have a staging environment for QA testing.
And a development environment where engineers are just breaking things locally on their laptops.
Exactly. Those are your environments. So the delivery token, which is often referred to as an access token, is cryptographically bound to one and only one of those specific environments.
Ah, okay. Meaning if a junior developer accidentally pushes their local environment file to a public GitHub repository,
Which happens all the time.
right, and their development delivery token is compromised, a bad actor couldn't use that specific token to scrape or impact the live production website?
They'd hit a brick wall. The token is entirely sandboxed to the development data.
That's incredibly smart.
And furthermore, we are specifically talking about the Content Delivery SDK here, which is structurally isolated from the management side of the CMS.
Meaning you can't edit things with it.
Exactly. The delivery token only grants read-only access. It is physically impossible to use this token to overwrite, delete, or modify any content in the actual database.
It's purely a one-way street.
Right. It is highly optimized solely for rapid data retrieval to serve the front-end UI.
So once that triad is passed into the initialization method, the SDK just kind of takes over.
It drives the car for you.
Yeah, instead of the developer having to manually construct this massive fetch request, deal with the authorization headers, handle network timeouts, parse the raw stream into a JSON object.
All that boilerplate code.
Right. The SDK exposes very clean declarative methods. The docs show methods simply named content type, entry, and query.
And this represents a massive shift from imperative networking logic to declarative data fetching.
How so?
Well, the developer simply declares what they want. They just type, give me the entry from the hero content type.
Just one simple line of code.
Yes. And under the hood, the SDK is assembling all the underlying REST calls, establishing the TCP connections, injecting the headers, and handling the promise resolution.
I think about it like having a really smart executive assistant.
Okay, I like that.
Because using raw HTTP requests is like having to manually dial a 20-digit international phone number from memory, listening for the dial tone, and manually routing it through a switchboard every single time you want a tiny piece of information.
It's exhausting.
But the SDK is the assistant. You just hit the intercom and say, hey, get me the profile for the hero named Batman. And the assistant handles all the routing protocols, the country codes, and just hands you the neatly parsed document.
That's exactly it. And the downstream effect of that abstraction is massive for team velocity.
Because they can move faster.
Yeah, it completely democratizes data access. Front-end UI developers don't need to be network engineers or back-end database administrators just to populate their application.
Right. They can stay entirely focused on what they do best.
Which is component architecture, state management, and rendering highly performant visual experiences.
Well, I'm stuck on something, though, looking at these curriculum notes.
What's that?
We just praised the JavaScript SDK for being this brilliant, simple one-line fetch. It brings you the document effortlessly.
Right.
But the very next section of the technical documentation introduces a totally different way to fetch data.
GraphQL.
Yeah, using the GraphQL API and testing it with Postman. Why would we abandon that beautiful, simple SDK abstraction to write custom GraphQL queries?
That's a great question.
Aren't we just trading one form of manual labor for another?
It might look like that at first glance, but it's actually a very intentional trade-off between implementation speed and payload optimization.
Okay, break that down for me.
Well, the standard JavaScript SDK typically wraps around a REST API architecture. And in a REST paradigm, when you ask for an entry, let's stick with the superhero profile example, the server fulfills the request by returning the complete data object defined in the database.
The whole thing, meaning if the superhero entry has a name, a 10,000-word biography, an array of 50 high-resolution image URLs, and a massive list of related comic book IDs, I get all of it.
You get the entire tree. Every single branch.
Wow.
Now, if you are rendering the main detail page for that specific hero, that's fine. You probably actually need all that data.
Sure, for the full bio page.
But consider the architecture of a mobile application's home screen, or even a smartwatch interface.
Where space is super limited.
Exactly. In those environments, you are usually just displaying a scrolling list or a directory of, say, 100 heroes.
In that view, I only need the hero's name and maybe a tiny thumbnail avatar, nothing else.
Right. But if you use the standard REST approach to fetch that directory of 100 heroes, you are downloading 100 full-weight entries.
Oh, I see the problem.
You are pulling megabytes of text and metadata across the cellular network, dumping it all into the device's memory heap, and then your front-end code throws 95% of it away just to render the name and the thumbnail.
That's incredibly wasteful. So you are wasting the user's mobile data plan, you're increasing the latency of the initial load, and burning their battery just parsing a massive JSON tree that never actually hits the screen.
It is a severe performance bottleneck, and it's known in the industry as overfetching.
Overfetching. Makes total sense.
And GraphQL was designed specifically to solve this exact problem.
By doing what?
It shifts the power from the server deciding what data to return to the client explicitly dictating the shape of the required data.
Ah, so you ask for exactly what you want.
Precisely. With GraphQL, you write a query that essentially says, fetch the list of heroes, but only return the name field and the thumbnail field. Drop everything else before it ever leaves the server.
So the server processes the query, strips the fat, and sends back a perfectly tailored, super lightweight JSON response.
The precision is incredible.
It really is. But looking at the examples here, the developer experience of writing raw GraphQL queries can be a little intimidating.
It is a learning curve, yes.
Because the syntax is very different from standard JavaScript.
Yeah, which is why the curriculum heavily emphasizes using Postman to build and test these queries before writing a single line of actual application code.
Postman acts as a dedicated testing sandbox, right?
Exactly. You configure it by pointing it to the Contentstack GraphQL endpoint URL, and then you inject your API key and delivery token into the headers.
Just like we talked about earlier.
Right. But the feature that truly transforms the developer experience here, the real magic of GraphQL and Postman, is introspection.
Introspection. Okay, in a psychological sense, it means looking inward. How does an API look inward?
Well, in GraphQL architecture, the API is strictly typed. It is a rigid schema that defines exactly what content types exist, what fields are inside them, and whether those fields are strings, integers, arrays, whatever.
It knows its own shape.
Exactly. Introspection means the API is literally capable of being queried about its own structural schema.
That's wild.
So when you connect Postman to the endpoint, Postman sends a hidden query asking, hey, what does your data model look like?
And the API responds with its own blueprint. It says, I have a hero type, and within that, I have a name field, which is a string, and an age field, which is an integer.
Precisely. And because Postman instantly downloads and parses this schema blueprint, it unlocks intelligent autocomplete.
Oh, that's huge.
It changes everything. As a developer starts typing a query, Postman suggests the exact field names available in the Contentstack repository.
It eliminates all the guesswork.
You don't have to toggle back and forth between the CMS dashboard and your code editor to try and remember if you named the field hero name or just name.
Postman just knows.
Postman knows, and it catches syntax errors before you even execute the request.
Okay, so the architectural trade-off here is super clear now. You use the SDK's built-in REST methods when you need rapid development, and you are utilizing the full entry anyway.
Right, like for a detail page.
But you pivot to GraphQL when you have strict bandwidth constraints, complex relational data, or you need absolute surgical precision over the payload size to ensure client-side performance.
Exactly. You pick the right tool for the job. But optimizing the size of the payload only solves half of the performance equation.
Right, because we still have to deal with the physical reality of the internet.
The speed of light.
Yeah, the speed of light. Because even if our payload is perfectly optimized down to 2 kilobytes using GraphQL, if the origin server is sitting in a data center in New York and the user opening the application is standing on a train platform in Tokyo, those 2 kilobytes still have to physically travel across undersea fiber optic cables spanning the globe.
Yeah, latency is unavoidable in that scenario.
The physics of distance is real.
It is the hardest problem in distributed systems, frankly. And it's why the curriculum pivots from querying data to the architecture of delivering data.
Specifically the CDN, right? The content delivery network and all the highly sophisticated caching layers involved.
Exactly.
The documentation points out that Contentstack inherently utilizes a global CDN to serve content from edge locations. For you listening who might be newer to infrastructure, what does the edge actually mean in this specific context?
So the edge is essentially the perimeter of the network. It's the physical points of presence that sit as close to the end user as geographically possible. A CDN is a massive distributed mesh of servers located in hundreds of data centers worldwide.
So they're everywhere.
Everywhere. So when your user in Tokyo opens the Next.js app, the DNS routing doesn't send their data request all the way back across the ocean to the primary database in New York.
That would take forever.
Right. Instead, it routes the request to a CDN node sitting in a Tokyo data center just a few miles away from them.
And caching is the mechanism that allows that Tokyo server to actually fulfill the request, right?
Yeah.
Because the master database isn't in Tokyo.
Right. Caching is simply storing a temporary rapid access copy of the data.
Okay, so walk me through a request.
So when the very first user in Tokyo requests the superhero directory, the local Tokyo Edge node checks its memory and realizes, uh-oh, I don't have this data.
This is what we call a cache miss.
Exactly. So that Edge node must then reach across the ocean to the origin server in New York, retrieve the JSON payload, serve it to the user, and crucially save a copy of that payload in its own local cache.
So that fourth user basically takes the latency hit. They wait the extra half second.
Right, they blaze the trail. But when the next 10,000 users in Tokyo open the app an hour later, the Edge node says, oh, I already have this JSON in memory.
A cache hit.
Yes. It serves the payload locally. The request never leaves Japan, and the response time drops from hundreds of milliseconds down to just 10 or 20 milliseconds.
That's incredibly fast.
And that is standard CDN behavior. But Contentstack actually implements an advanced architectural layer, specifically to protect the origin database from catastrophic overload.
Oh, I noticed this in the technical diagrams. It's called the shield server.
Yes.
The diagram shows the edge nodes on the outside, then the shield server layer, and finally the origin database in the center. What failure scenario does the shield server actually prevent?
It prevents a phenomenon known in systems architecture as the thundering herd problem.
The thundering herd? That sounds terrifying.
It is for a database. Imagine you just launched a highly anticipated marketing campaign globally. Suddenly, edge nodes in Tokyo, London, Sydney, Mumbai, and Berlin all receive requests for a new GraphQL payload simultaneously.
And none of them have it in cache yet because it's brand new.
Exactly.
Yeah.
So they all experience a cache miss at the exact same millisecond.
Oh, no.
And standard edge nodes are relatively dumb. Without a shield layer, every single edge node worldwide would independently open a connection and ping the origin server in New York demanding the exact same piece of data.
So if you have hundreds of edge nodes, the origin server is suddenly hammered with massive concurrent traffic just to calculate and receive the exact same response hundreds of times.
Right. The database CPU spikes, latency degrades globally, and in worst-case scenarios, the origin crashes entirely under the load of its own delivery network.
That's the thundering herd. So enter the shield server.
Right. The shield server acts as a centralized buffer, physically located very close to the origin server in New York.
Okay, so it's a gatekeeper.
Exactly. When the edge nodes in Tokyo, London, and Sydney experience their cache misses, they don't talk to the database directly anymore. They talk to the shield.
And what does the shield do?
The shield intercepts all those simultaneous requests. It checks its own internal cache, realizes the data is missing, and then here's the truly brilliant part over. It collapses all those identical requests into a single unified query.
Wow. So the shield turns around to the origin database and says, look, I know 50 different global nodes are asking for this right now, but I'm only going to ask you once. Give me the payload.
Exactly. The origin processes the request exactly one time, hands it to the shield, and immediately goes back to baseline resource usage.
Crisis averted.
Then the shield caches the response itself and distributes it outward to Tokyo, London, and Sydney. The database is entirely insulated from global traffic spikes.
I mean, that architecture is incredibly resilient.
It really is.
But caching has always had this Achilles heel, hasn't it?
Stale data.
Right. If the data is cached in Tokyo and the content editors in New York update the superhero's profile to fix a glaring typo, the users in Tokyo will continue to see the old data with the typo until the cache expires.
Yeah. Managing cache time to live, or TTL, and writing custom invalidation scripts is historically one of the most error-prone, frustrating parts of DevOps.
Stale data is the enemy of a dynamic web application.
You want the speed of the edge cache, but you require the absolute real-time accuracy of a dynamic database.
Which feels like a paradox. Achieving both is the holy grail.
But the curriculum details how Contentstack achieves this, and it's through automated event-driven cache purging.
Okay, so how does the system know when to purge? Is it just like checking back with the origin every few seconds to see if anything changed?
No, because polling the origin constantly completely defeats the purpose of caching. It would overload the server anyway.
Right, that makes sense.
It's an event-driven push model. Because the headless CMS and the CDN delivery layer are tightly coupled in the Contentstack ecosystem, the whole system acts as a unified state machine.
Okay, so what's the trigger?
The exact moment a content editor clicks the publish button in the CMS interface It triggers a system-wide webhook.
An execution signal.
Yes. The origin database commits the update and instantly fires a purge signal targeting that specific entry's unique identifier.
So it's not purging the whole site, just that one piece of content?
Exactly. That targeted signal propagates outward through the network, hits the shield server, and fans out to every single edge node globally.
And they dump it.
The nodes immediately dump that specific stale JSON object from memory.
So the very next user who requests the data in Tokyo triggers a fresh pull from the origin.
Exactly. So the developers building the Next.js app don't have to write a single line of cache invalidation logic.
That is massive.
They don't have to configure complex caching headers or manually flush edge networks. They just get the millisecond performance of a static edge cache with the real-time consistency of a direct database connection.
The infrastructure just handles the state synchronization seamlessly.
It does.
But, fast delivery is really only part of the equation here. Even if the data arrives in 10 milliseconds, what happens if the data is just irrelevant to what the user actually requested?
Right. Serving the wrong data quickly isn't very helpful.
Exactly. Which brings us to querying and server-side filtering via the Content Delivery API or the CDA.
This is a crucial step.
Because if we have a database containing 10,000 unique products, or hero profiles in our case, we rarely want to retrieve all of them at once. We need powerful filtering mechanics to isolate subsets of data before it ever hits the CDN.
And filtering is fundamentally a database operation. The CDA exposes dedicated query methods that allow the developer to perform complex index scans right at the edge.
The documentation highlights a few core filters. There's a contained-in query, which matches a field against an array of valid parameters.
Right. For instance, querying for heroes whose origin city is either Gotham, Metropolis, or Star City.
And then there are comparative where queries finding entries where a numerical power level is greater than a certain threshold or a price is less than $100.
You also have native sorting methods, instructing the API to return the filtered results strictly ordered by creation date or alphabetically by title, ascending or descending.
Now, I have a theoretical question here.
Go for it.
Why rely on the Content Delivery API to execute this sorting and filtering?
What's the alternative?
Well, let's say I have a directory of 5,000 heroes. Couldn't I just fetch the entire block of 5,000, cache that massive JSON object at the edge, and use a lightweight JavaScript function running in the user's browser to instantly filter and sort the data locally?
So without ever pinging the API again.
Yeah. Why not do that?
You are touching on a very common and very heavily debated architectural topic: server-side versus client-side processing.
Right.
While fetching the entire block seems efficient from a pure network request perspective because you only make one request, it places a massive computational burden on the client device.
On the user's actual hardware.
Exactly. And this is a trap developers fall into. We often develop applications on high-end laptops with massive amounts of RAM and incredibly fast multi-core CPUs.
So it feels fast to us.
Right. If you load a 5,000 item array into memory on an M-series Mac and run a JavaScript filter and sort method on it, it happens instantly. You don't even notice it.
But the real world isn't composed of high-end developer machines.
Not at all. The real world is a user opening your web app on a 3-year-old Android smartphone with limited memory and a thermal-throttled CPU while they're running 10 other apps in the background.
Oh, man.
Yeah. If you force that device's browser to parse a 5-megabyte JSON string into a JavaScript object tree, allocate memory for it, and then run complex algorithmic sorts on it, the browser thread will literally block.
The UI freezes?
The UI will freeze, the scrolling will stutter, and the device battery will visibly drain while it churns through the data.
So by doing it on the client, you are offloading the computation to the weakest link in the chain.
Precisely. By pushing the filtering and sorting back up to the Content Delivery API, you are leveraging highly optimized, multi-threaded enterprise database servers to do the heavy lifting.
They can handle it.
The database executes the query in fractions of a millisecond and sends down a perfectly sorted array of just the 20 items the user actually needs to see right now. The mobile device just has to paint the pixels on the screen.
Which is what it's good at.
Exactly.
And speaking of those 20 items, there is a specific parameter in the CDA that caught my attention here. The include count feature.
Ah, yes.
It explicitly returns the total number of entries that match the query right alongside the paginated data. And the notes say that when you're building out pagination, knowing your total hit count is critical.
Absolutely critical.
Because without include count, your Next.js front end is basically flying blind. It doesn't know whether to render 5 pages of results or 50 pages.
Yeah, pagination is a surprisingly complex systems challenge.
Walk me through it.
Let's say you query the API with a limit of 20, because you only want to display 20 items per page on your gallery.
Makes sense.
The server dutifully returns exactly 20 items. But the client application has absolutely no idea if there are 21 total items in the database or 20,000.
It's just a black box.
Right. And if you don't know the total, you literally can't calculate how many page numbers to generate in the footer navigation at the bottom of the screen.
So what does include count actually do under the hood?
The include count parameter forces the backend database to execute 2 operations simultaneously.
Okay.
First, it runs the standard query with the limit and offset to grab the specific 20 documents for that page.
Right, the data payload.
Second, it runs a full index count on the query parameters to determine the absolute total of matching records. And then it bundles both the array of 20 documents and the integer of the total count into one single JSON response.
So the front end gets everything it needs at once?
Yes. The front-end Next.js component simply takes that total count, divides it by 20, rounds up, and instantly knows exactly how many pagination links it needs to render.
That is so clean.
It is.
But we've spent a lot of time analyzing text data here. JSON payloads, strings, numbers, filters.
Right.
But text is computationally lightweight. The heaviest assets traversing the network, the elements that truly bog down web performance and destroy layout shifts, are media assets.
Images.
Yeah, images. How does this architecture prevent our ultra-fast CDN from getting completely choked by massive image files?
Text data is measured in kilobytes. A high-resolution hero image is measured in megabytes. Managing the lifecycle of these assets requires an entirely different system, which is why Contentstack utilizes a dedicated images API.
A completely separate pipeline.
Yes.
The curriculum states this API accepts source files up to a massive 700 megabytes.
It does.
That is not web optimized. A 700 megabyte file is raw, uncompressed professional photography or massive digital artwork.
And that is a very deliberate philosophical choice by the platform.
Why?
The system demands that content editors and designers upload the highest possible quality original asset, the master file. They should not be tasked with manually creating web-optimized derivative files.
Because it's a waste of their time.
Exactly. The Images API is designed to handle all of the processing and optimization programmatically on the fly when the asset is actually requested by the client.
This represents a massive shift in workflow.
Huge.
Think about traditional environments. A web designer has to open the master file in Photoshop. They crop a specific 1:1 square version for the mobile thumbnail.
Then they crop a 16:9 widescreen version for the desktop hero banner.
Right, and they have to compress both of them manually, try to balance the quality, save them as separate files, upload them to the server, and then link them individually in the CMS.
It's a nightmare. And think about what happens if the UI team redesigns the site 6 months later.
Oh, boy.
What if they decide the mobile thumbnails should be 4:3 rectangles instead of 1:1 squares?
The entire manual workflow has to be repeated for every single image in the database.
It is completely unsustainable at an enterprise level.
But the Images API solves this by using URL query parameters to execute these transformations instantly.
Exactly. The front-end code doesn't just request the raw image URL, it appends instructions to the URL.
Okay, give me an example.
So if the Next.js component is rendering the mobile view, it requests the image URL and appends .width 200 and crop 1.1.
And the desktop component?
The desktop component requests the exact same source URL, but it appends .width 1200.
So the API server intercepts that request.
Right. It takes the 700 megabyte master file stored securely in the vault, executes an in-memory image processing algorithm to resize and crop the pixels exactly as requested by the URL, compresses the result, and streams it down to the user.
But wait a minute.
Wait.
Image processing is highly CPU intensive.
Very.
Recalculating the pixels of a massive image requires serious compute time. If the API server is doing this on the fly for every single image load, wouldn't that introduce massive latency for the end user?
Oh, if the server had to process the image from scratch for every single request, the whole system would collapse immediately.
So how does it survive?
This circles right back to the architecture of the CDN we discussed earlier. The on-the-fly processing only happens exactly one time per unique URL string.
Ah. The caching layer applies to the derivative images as well.
Exactly. When the very first user visits the mobile site and their browser requests the image width, that 200 and crop 1.1, the image server does spend a few dozen milliseconds processing that new derivative.
You take the initial hit.
Right. But as that new tiny image flows outward through the CDN, the edge nodes cache that specific URL string along with the optimized image payload.
So when the next million users load the mobile site, they are served the pre-calculated 200-pixel image directly from the edge cache in 10 milliseconds.
The origin server is never bothered again. You get infinite design flexibility for your front-end engineers, zero manual processing for your content team, and edge speed delivery for your users.
That is just brilliant.
Furthermore, the API supports format auto-negotiation, primarily through the format web parameter.
WebP, that's the highly advanced image format developed by Google, right?
Yes, it provides significantly superior lossless and lossy compression compared to older formats like JPEG or PNG.
But not all legacy browsers support WebP.
Right, especially older Safari versions or Internet Explorer.
So if you force WebP everywhere, couldn't that break the image for users on older devices?
It could, and that's where the intelligence of the API really shines. When the browser requests the image, it sends an accept header detailing what formats it actually understands.
Okay.
The image's API reads that header. If the browser says it supports WebP, the API dynamically converts the image to WebP, drastically reducing the file size, often by 30% or more, without any visible quality loss.
And if the browser is older?
If the browser doesn't support WebP, the API gracefully falls back to serving the optimized JPEG.
Wow.
It ensures maximum performance for modern devices while maintaining complete backwards compatibility for older ones, automatically.
It's a remarkably sophisticated pipeline.
It truly is.
So we've established all the foundational tools here. We have the declarative SDK, the precision of GraphQL, the global distribution via CDNs, server-side filtering, and real-time media optimization.
All the building blocks.
Right. Now, the curriculum pivots from abstract data concepts to actual page construction.
Where the rubber meets the road.
Exactly. How do we take all these APIs and build a tangible UI? And the documentation starts with the architecture of the detail page.
In application development, a detail page is the standard architectural pattern for displaying a single specific entity.
Okay, so if you are building an e-commerce site, the detail page is the individual product listing.
Exactly. And in our context of a superhero directory, it is the dedicated profile page for a single hero, like Wonder Woman.
But to populate that page, the Next.js application needs to know exactly which entry to fetch from the API. You need an identifier.
Yes. Developers generally rely on either a rigid unique ID, a UID generated by the database, or a more human-readable URL slug.
A URL slug, that's the dynamic portion of the web address that uniquely identifies the resource, right?
Right. So in a URL like yoursite.com, here's Wonder Woman, the string Wonder Woman is the slug.
And it maps directly to a specific field in the database entry.
Correct. The curriculum illustrates how this works within a Next.js dynamic route file, which is typically named something like slug.tsx.
The brackets indicate to the framework that this route is highly dynamic.
Yes. So when the user navigates to that URL, Next.js extracts the string Wonder Woman, passes it into a helper function, and triggers the SDK.
And the SDK fires a query targeting the hero content type.
Specifically applying a where filter, where the slug field exactly matches Wonder Woman.
And the Contentstack API returns the single JSON object containing all the data for that specific profile.
Exactly. At that point, it just becomes a mapping exercise.
How so?
The React component basically acts as a structural mold. The developer takes the properties from the JSON object and binds them to the HTML tags.
So entry.title is bound to the h1 heading tag.
Yes. The image URL is bound to an MLG tag, complete with all those optimization parameters we just talked about.
It is the purest form of decoupling content from presentation.
It really is. But there is one specific data type within the detail page architecture that requires a much deeper analysis.
What's that?
The JSON-rich text editor, or JSON-RT.
Oh, yes. The documentation spends a lot of time on this. Because most standard rich text editors in older CMS platforms are essentially just YSIY HTML generators.
What you see is what you get.
Right. An editor highlights a sentence, clicks the bold button, and behind the scenes, the editor just wraps that text in strong or BHTML tags and saves the entire block as a massive HTML string in the database.
Which is how it was done for decades.
But Contentstack explicitly stores this content as raw JSON. Why is JSON vastly superior to HTML strings for rich text?
Storing HTML in a database is an architectural anti-pattern in a headless ecosystem.
An anti-pattern. Why?
Because HTML is strictly a presentation format. It dictates exactly how a web browser should render the document. But a headless architecture is fundamentally omnichannel.
Right, right. You aren't just building a website anymore.
Exactly. You might be piping this superhero biography into a Next.js web app, sure. But you might also be sending the exact same payload to a native iOS application written in Swift, or a smartwatch interface, or an audio-only voice assistant.
Oh, I see. An iOS application doesn't natively render HTML strong tags.
Not without a web view, which is clumpy. And a voice assistant has absolutely no concept of an HTML block quote or an H2 heading.
It just reads audio.
Right. If you send them an HTML string, their parsers will break, or you will have to write brittle, complex reject scripts on the client to try and strip the tags out.
So the JSON-RT abandons HTML entirely.
It saves the content as structured data specifically, an abstract syntax tree, or AST.
An abstract syntax tree.
Yes, an AST represents the semantic structure of the content without dictating the presentation at all.
Okay, give me an example of what that looks like.
So the JSON payload doesn't say, make this bold. It says, here is a node of type paragraph. Inside it, there is a text node with a value of Wonder Woman, and this node possesses a mark of type bold.
Wow. It is pure structured metadata.
Exactly.
And how does the Next.js application turn that abstract tree back into visual text on the screen?
It uses a process called serialization.
Serialization?
The front-end framework receives the JSON AST and passes it through a serialization function. The function traverses the tree node by node.
Okay.
If it's running in a Next.js web environment, the serializer is specifically configured to map a paragraph node to a p tag and a bold mark to a strong tag.
But if that exact same JSON tree is fetched by the iOS app,
then the native Swift serializer walks the tree and maps the paragraph node to a native UI text view component with a bold font weight applied.
that is incredible. The content is truly decoupled. It adapts natively to whatever environment is rendering it.
And that structural purity also unlocks immense extensibility for the content editors themselves.
How?
Because the rich text area is just generating abstract JSON nodes, developers can inject custom interactive plugins directly into the editor interface.
Oh, the documentation mentions this. Instead of just text, you could embed a custom Cloudinary plugin right in the middle of a paragraph.
Exactly. The editor clicks a button, searches their external digital asset management system, and drops a proprietary asset right into the flow of the text.
And in the back end, that plugin simply generates a custom JSON node in the AST containing the asset ID.
Yes. And the front-end serializer sees that custom node and knows to render a specific video player component at that exact point in the document.
It basically blurs the line between text editing and full-page composition.
It makes the editor infinitely powerful.
Okay, so the detail page is a universal pattern. Get the slug, fetch the entry, map the data, serialize the AST.
Check, check, check.
But an application requires navigation. We need a way to browse multiple entries, which brings us to the architecture of the gallery page.
The gallery page completely inverts the data fetching logic.
Right, instead of requesting a single entry based on a unique identifier, it requests a collection.
This utilizes the find method in the SDK, or a broad GraphQL query, to return an array of entries.
But as we discussed earlier regarding payload optimization, we don't want the full massive JSON object for every hero if we are just building a gallery grid.
No, we just need the summary data.
The architectural pattern here is the summary card, right?
Yes. The Next.js application iterates through the returned array. For each object, it extracts a highly specific subset of properties, usually just the hero's name, a 300-pixel optimized thumbnail from the Images API, and the URL slug.
And it passes those properties into a reusable card component.
Exactly. The user clicks the card, the Next.js router reads the slug, and navigates them to the detail page.
That makes perfect sense for a standard grid of items, but modern applications rarely feature simple, static grids anymore.
Very true.
A marketing landing page, for example, is highly complex. It might have a massive hero banner at the top, followed by a carousel of featured products, followed by a 2-column text layout, followed by the actual gallery grid, and ending with a newsletter sign-up form.
A standard landing page, yeah.
So how does the front-end code handle a gallery page if the layout is entirely dynamic?
This introduces one of the most powerful paradigms in headless content modeling. Modular blocks.
Modular blocks.
It fundamentally changes how content is structured and consumed.
It sounds like building a page out of Lego bricks instead of using a rigid single-piece mold.
That is the exact intent. In a legacy CMS, A page template is rigid. You have a title field, a body field, and an image field.
And if the marketing team wants to add a video carousel in the middle of the body text,
They have to submit a ticket to the engineering team to rewrite the database schema and the page template.
which takes weeks.
Right. But with modular blocks, the database field isn't a single string of text. It's an array that can hold a dynamic sequence of different predefined component schemas.
So the engineering team defines the Legos.
Yes. A hero banner block, a video block, a text block, a gallery grid block. They define them and then hand that bucket of Legos to the content editors.
And the editors can dynamically add, reorder, and remove these blocks in the CMS interface without any technical intervention.
Exactly. They can build a page that is just a title in a grid, or they can build a massive complex landing page with alternating banners and videos.
The editorial flexibility is incredible, but I have to look at this from the front-end developer's perspective.
Go on.
If the content editor has infinite freedom to stack blocks in literally any order, the JSON payload returned by the API is completely unpredictable.
It is. It's a dynamic array of different object types.
So how does the Next.js application know how to render a page when it doesn't know what blocks are coming?
It requires a highly decoupled component architecture on the front end, specifically utilizing what's called a polymorphic rendering pattern.
Polymorphic rendering, okay.
The Next.js application receives the array of blocks from the API. It then runs a map loop over that array.
And inside the loop, it inspects each block individually.
Yes. Each block in the JSON array contains a property, usually called something like type name or content type UID, that identifies its schema.
Oh, I see.
Inside the loop, the developer writes a switch statement or dynamic component resolver.
So the logic basically says, if the type name is hero banner, dynamically import and render the hero banner component, passing the block's data as props.
Exactly. And if the type is video carousel, render the video component.
So the code just iterates through the array, resolving each block type to a specific isolated React component, and stacks them vertically on the screen exactly as the editor arranged them in the CMS.
You got it. This one-to-one mapping between the back-end modular block schema and the front-end Next.js React component is the epitome of clean, scalable architecture.
It enforces a strict separation of concerns.
Absolutely. Because the code for the hero banner is entirely self-contained in its own file. It doesn't bleed into the code for the video carousel at all.
Which isolates maintenance.
Exactly. If a bug is reported in the video carousel, maybe the autoplay isn't working. The developer knows exactly which single file to open. They don't have to decipher thousands of lines of intertwined spaghetti code in a massive page template.
Furthermore, it enables safe extensibility.
Yes. If the marketing team demands a completely new type of block, say, a live Twitter feed, the developer just defines the new schema in Contentstack, creates a single new Twitter feed component in the code base, and adds one new case to the switch statement.
And the rest of the page architecture remains completely untouched.
You can deploy a major new feature with zero risk of breaking the existing layouts.
It is a beautifully decoupled system. But, to seamlessly loop through these dynamic structures on the front end, the back-end database must be meticulously architected.
It has to be pristine.
Because if the foundation is flawed, the decoupled UI components will just fail to render, which leads us directly into the discipline of content modeling and design patterns.
Data architecture is honestly the most critical phase of a headless project. The decisions you make during content modeling dictate the complexity of your front-end code and the performance of your API queries for years to come.
No pressure.
Right. The documentation highlights several specific patterns to enforce consistency, starting with global fields.
What architectural problem do global fields actually solve?
They solve the problem of schema redundancy, adhering to the fundamental engineering principle of DRY. Don't repeat yourself.
Okay, give me an example.
Let's consider SEO metadata. Every single public-facing page in your application, whether it's a hero detail page, a gallery landing page, or a simple blog post, requires SEO properties.
Right. A meta title, a meta description string, and an image URL for open graph social sharing.
Exactly. Now, if you are building the content types manually, you would have to manually recreate those three exact fields inside the hero content type, then recreate them inside the blog content type, and then recreate them inside the landing page content type.
And if you accidentally name the field meta description in the hero type, but mistype it as metadesk in the blog type,
your front-end SEO component will crash when it tries to query the data because the schema is inconsistent.
oh, that's bad. So global fields fix this.
Yes. Global fields allow you to define a schema snippet centrally. You create a global field entity called SEO fields containing the title, description, and image parameters once.
And then?
Then, you simply drag and drop a reference to that global field into any content type that requires it.
You build the schema logic once and inherit it globally.
It guarantees absolute schema consistency across your entire data model, meaning your front-end components can rely on a predictable data shape regardless of what page type they're rendering.
That is elegant. Now, the curriculum introduces another core pattern, reference fields.
Ah, yes.
These are used to create relationships between distinct entries in the database. For example, if we have a superhero named Superman, we can use a reference field to link his profile directly to a separate entry for the Justice League team.
In traditional relational database architecture, this is analogous to a foreign key constraint. It allows you to maintain a single source of truth. You do not manually type the string Justice League into the profiles for Superman, Batman, and Wonder Woman.
Because if the team name changes or you want to update the team's logo, you would have to manually find and update every single hero profile that mentioned them.
Instead, you create one central team entry. The hero profiles utilize a reference field that point to the unique ID of that team entry.
So if the team data changes, you update the central entry once, and the change instantly reflects across every referenced profile.
Exactly.
That sounds incredibly powerful. Honestly, if I'm architecting a new platform, I want everything connected. I want heroes referencing teams. I want teams referencing their headquarters. I want headquarters referencing specific cities and cities referencing entire universes.
Oh boy.
I want my data perfectly interconnected in a massive, elegant, logical graph.
And right there, you have just articulated the single most dangerous architectural trap in headless CMS design.
Oh, I walked right into it, didn't I?
You did.
What is the fundamental flaw with deeply interconnected references?
The curriculum provides a severe warning against exactly that impulse. While heavy normalization works well in raw SQL databases doing backend analysis, it is a disaster for a content delivery API focused on front-end performance.
Why is that?
The rule of thumb in headless modeling is keep relationships as flat as possible.
But if the data is logically connected, shouldn't the database reflect that reality?
Well, let's follow the data flow for your idea. When the Next.js application requests the Superman profile to render the detail page, it pings the API.
Right.
The API retrieves the Superman JSON document, but the API sees that the Superman document contains a reference field pointing to the Justice League entry.
Okay.
By default, the API does not retrieve the related document. It only returns the unique ID of the reference.
So the front end receives the Superman data, but the team property just says reference seed 12345.
Yes. To actually display the name Justice League on the screen, your front-end code has to fire a second, entirely separate API request back to the server just to resolve that ID.
Oh, I see.
You've just introduced an N+1 query problem, effectively doubling your network latency.
But wait, Contentstack's API allows you to resolve these references on the server side using the include query parameter, right?
It does. You can instruct the API, fetch Superman, and simultaneously pull in the full data object for the reference team.
Okay, so the server resolves the relationship, and I get one unified JSON payload back. That solves the latency issue, right?
It solves the network latency, but look at the exponential complexity of your proposed graph architecture.
What do you mean?
You wanted the hero to include the team to include the headquarters to include the city, and the city to include the universe.
Oh, no.
Your front-end application now has to send a massive, highly complex recursive query to the API.
Right.
The origin database has to perform deep, multi-level relational table joins across 5 different content types just to fulfill a single-page request.
The database compute time skyrockets.
And worse, the final JSON payload returned to the client isn't a few kilobytes. It's a massive, deeply nested tree containing hundreds of irrelevant fields about the universe's origin story, just because you wanted to display the name of a city on a hero's profile.
The parsing overhead on the client device would be catastrophic.
The relationships create a web of rigid dependencies that bloats the payload and destroys performance.
So deep reference chains are an anti-pattern.
Yes. The architectural best practice is denormalization. Keep the data flat.
Okay, so when should you use them?
Only utilize reference fields when the target content is a complex, independent entity that is heavily reused and managed by a different editorial team.
So if you just need the name of a city.
Don't create a city content type and reference it. Just put a simple text string directly into the hero profile. Prioritize the speed of delivery and the simplicity of the front-end integration over theoretical database purity.
That is a hard-earned piece of engineering wisdom.
It really is.
It highlights how the decisions made in the CMS dashboard directly impact the milliseconds of load time experienced by the end user on their phone.
Everything is connected.
So we've traced the entire data flow today. We've fetched with the SDK. We've optimized payloads with GraphQL. We've distributed via edge CDNs. We've filtered at the server level.
We've dynamically transformed media.
Right, and we've architected pristine detail and gallery components driven by decoupled content models. There is really only one phase left in the development lifecycle.
We have to ship the application to the public.
Yes. Writing the Next.js code on your local laptop is only the first step. Getting that complex front-end application compiled, optimized, and deployed onto secure, scalable infrastructure so the world can access it. Well, historically, that has been an immensely frustrating process.
Involving dedicated DevOps teams, complex CI/CD pipelines, Docker containers, and intense server configuration.
But the curriculum introduces Contentstack Launch as the final piece of the puzzle here. It frames Launch not just as a hosting provider, but as a fully integrated front-end delivery platform deeply woven into the headless ecosystem.
Launch is designed to completely eradicate deployment friction. It is a GitOps-driven deployment engine.
GitOps, meaning it relies on your version control system.
Exactly. You don't FTP files to a server anymore. You connect your Next.js project's GitHub, GitLab, or Bitbucket repository directly to the Launch dashboard.
Okay, establishing the repository connection is straightforward. But the immediate architectural question that comes to mind is security, specifically environment variables.
Right.
Because my local Next.js codebase relies on an .env file containing my specific Contentstack API key, and crucially, that environment-specific delivery token we discussed at the very beginning.
The read-only token.
Yes, and I absolutely cannot commit that .env file to a public or even a shared private Git repository. It's a massive security vulnerability.
Never commit secrets to code.
So how does the live production server actually know how to authenticate with the database if I don't give it the file?
The secure injection of environment variables is a core feature of an integrated CI/CD pipeline.
Okay, how does it work in Launch?
Instead of putting them in code, you navigate to the Contentstack Launch dashboard and define your key value pairs directly within their secure vault.
Oh, I see.
You explicitly tell the Launch project, when you are building the production environment, use this specific production delivery token. When you are building the staging environment, use the staging delivery token.
So the keys exist safely in the cloud platform, entirely separate from the code base itself.
Exactly.
So how is the actual deployment triggered? Do I have to click a build button every time I update the UI?
No, it is entirely automated via webhooks. It is an immutable deployment pipeline.
Automated how?
You utilize your standard Git workflow. An engineer writes a new feature branch on their laptop, tests it, and merges that code into the main branch of the repository. The exact moment that merge commit hits the repository, GitHub fires a webhook signal to Contentstack Launch.
Ah, an event trigger.
Launch intercepts that signal and instantly provisions an isolated ephemeral build container. It pulls down the latest code from the main branch, securely injects the production environment variables from its vault, and executes the framework's build command.
Which in this case is next build.
Exactly. The build process compiles the React components, optimizes the JavaScript bundles, and generates the static HTML assets.
And once it's done?
Once the compilation is successful, Launch automatically distributes those immutable build assets across its own global edge network and dynamically updates the DNS routing. The new version of the application goes live instantly with zero downtime.
And what if the build fails? Like, what if someone pushed a syntax error?
If the build fails, Launch simply aborts the deployment. The previous live version remains completely untouched, ensuring absolute stability for your users.
It functions exactly like an automated assembly line.
It really does.
The engineer drops the finalized blueprint onto the conveyor belt by pushing to Git. Launch acts as the factory. It automatically sources the parts, securely installs the engine, paints the chassis, and literally drives the finished vehicle off the lot onto the public internet.
And the engineering team never touches a single Linux server configuration.
And importantly, the platform is framework agnostic.
Very true.
While our narrative has focused heavily on Next.js because it is the industry standard for React rendering right now, The launch pipeline natively understands and builds applications written in Vue, Gatsby, Nuxt, Svelte, or really any modern composable framework.
It abstracts away the infrastructure completely, allowing the team to iterate on the UI continuously.
What an incredible journey through the architecture of the modern web.
It's a lot to take in, but it's fascinating.
To summarize the massive paradigm shift we've explored today via the Contentstack developer documentation, we started by abandoning manual HTTP requests in favor of the declarative JavaScript SDK.
Learning how the triad of API keys and environment tokens strictly enforces security and blast radiuses.
We analyzed the critical difference between standard REST endpoints and the surgical precision of GraphQL, detailing how introspection allows tooling like Postman to instantly read the database schema to prevent overfetching on mobile networks.
We dive deep into the physical realities of global latency, exploring how edge CDN caching is shielded by buffer servers to prevent database thundering herds.
And how automated webhook-driven cache purging solves the ancient dilemma of stale data.
We looked at the performance imperative of server-side filtering via the Content Delivery API, shifting the computational tax of sorting and pagination off the user's mobile CPU and onto the enterprise cloud.
We saw how the Images API eliminates manual asset creation through on-the-fly, edge-cached parameter transformations and intelligent WebP format negotiation.
We mapped the exact architectural patterns for UI development. We moved past static HTML strings to embrace the JSON-rich text editor, utilizing abstract syntax trees for true omnichannel serialization across web, mobile, and IoT devices.
We tackled dynamic page compositions using modular blocks, highlighting the necessity of polymorphic React switch statements to keep component codes strictly isolated and maintainable.
We confronted the dangers of theoretical database purity, learning why denormalized flat content models outperform deeply nested reference chains that trigger cascading N+1 query failures.
And finally, we closed the loop with Contentstack Launch, replacing manual server administration with automated, GitOps-driven CI/CD deployment pipelines.
Every single one of these highly complex abstractions, the SDKs, the ASTs, the edge nodes, the build containers, they all serve a singular, unified purpose.
Which is to completely decouple the back-end data infrastructure from the front-end presentation layer.
Exactly. It frees the developers and the content creators from the friction of monolithic architecture, allowing them to focus purely on speed and user experience.
It is the definition of automated elegance. But as we look at how far the architecture has evolved, we have to look forward. We like to leave you, the listener, with a provocation, a thought experiment that builds upon the foundation of everything we've analyzed today.
What is the next logical step for a fully decoupled web?
Exactly. Think about the ultimate state of decoupling we just described.
Right. The content is structured purely as intent, JSON ASTs, and modular blocks sitting quietly in a headless database.
And the front-end UI consists of isolated dynamic React components that know how to render that intent.
Currently, a human developer writes the GraphQL query to fetch the block and maps it to the component.
But if the layout and the data are mathematically separated, how far are we from a future where artificial intelligence acts as the real-time orchestrator?
You mean skipping the static code base entirely?
Imagine a system that detects a user's specific context, their location, their device capability, their past browsing behavior, their current intent. In the milliseconds between the click and the page load, an AI model dynamically writes a highly custom GraphQL query targeting specific modular blocks, whilst simultaneously generating a unique, context-aware React UI component to render it.
It wouldn't just be serving personalized content. It would be architecting and deploying a completely unique software interface generated on the fly for every single individual user in real time.
The composable building blocks the APIs, the edge compute, the decoupled content they are already functioning in production today. We are simply waiting for the intelligence layer to learn how to stack them autonomously.
That is wild to think about.
From the legacy friction of manually laying HTML bricks and cropping Photoshop files to an ecosystem where AI architectures dynamically construct customized digital mansions of data for individuals in milliseconds.
It makes you realize that the incredible engineering we're implementing today might just be the foundational warm-up act for what comes next.
Thank you so much for joining us on this deep dive into the mechanics of the modern web. Keep exploring the architecture, keep questioning the abstractions, and keep building. We'll catch you on the next one.